Hello fellow problem solvers. So they're going to be doing the second part of our functional equation series, like an introduction to functions in competitive mathematics. So here I want to stress these three definitions. I frankly, at one point, so first let's see what the definitions are. The definitions are if a function from set A to set B, if it satisfies that for every x and y in A, that are different, f of x is different from f of y, then f is called injective or an injection, right? It says that really if you have these two sets, it means that every single element from A is mapped to a different element in B. Now, if a function is surjective, that's the injection. On the other hand, if for every element in B, there is something in A which maps to it, that function is called surjective. And if f is both injective and surjective, then it is called bijective. Now, these definitions, the actual names, injective, surjective, there's one-to-one, on-to, bijective, like these names, in my humble opinion, don't matter that much. I was on the Balkan Math Olympiad in 2016. And the first problem I think went along the lines of find all surjective or find all injective functions such that something is true. And I was not 100% sure whether like surjective was this or this, right? I might have mixed them up. But on the competition, I sent a question, because you can send a question at, I think in most competitions, but at the BMO, at the IMO, you can write a question and send it in the first half hour. And I just sent it and I wanted to make sure, like, which one was it really? Because you're not really helping me solve the problem by telling me a definition, right? So, and I sent in that question, and when I got back the response, I had assumed that either surjective is this. Like I saw the problem and I was like, okay, it's the first problem, probably it means this thing. And then I solved the problem, then I got it back and I was like, oh yeah, it's good. By that time, I'd already moved to other problems. So that's a little story for injection, surjection. And with these definitions in mind, we're going to try to prove two things, do these two separate problems. One is you have a function from A to A such that f of x is equal to x for every x in A. And we want to prove that f is bijective. And the second problem is going to be more old school, like more putting in stuff, trying to figure out like how to find all functions from the positive for natural numbers to the real numbers such that this is true and f of 1 is 2, f of 2 is 4. So first we're going to do this. I invite you to pause and try to do this for the next 10 minutes. And if you wanted to go ahead and try to do this as well, this one I invite you to pause for at least 20 minutes and try to work with it. That's an at least, really. So now let's start off with this problem. So what do we have? We have that f of x is equal to x, and we must prove both that this is injective and surjective. So what does it mean that it's surjective? It means that for every z that's in A, right, because that's the codomain. This is called the domain and the codomain. For every z that's in the codomain, we must prove there exists some t such that f of t is equal to z. Now, given this is our function, does there exist such a t? What is that t? The answer is, if we plug in for every z, for t is equal to f of z, we will have f of t is equal to f of z, which is by this equal to z, which says that f, and this proves that f is surjective. Now, if we want to prove it's injective, it means that the way we usually prove it is we say take two a and b such that f of a is equal to f of b. And if this implies that a is equal to b, then it's how do I say? Then it's injective. So here, what do we do with this? How do we connect this to this? Well, the answer is let this be equal to some c. Now, what is f of c? Well, f of c is on one hand equal to f of a, which is by this equal to a. On the other hand, this is equal to f of b, which is by this equal to b. So we have this thing right here, implies f of c is both a and b, which implies that a is equal to b, and ergo, the function f is bijective. This is a useful fact to know. This comes up in problems sometimes when you want to prove injectivity or surjectivity. The reason these things are important and valuable is because in injectivity, what you'll have a lot of f's on both sides, and then if you can just like separate out two f's of something are equal, then you can get rid of the f's if you have injectivity. And that's pretty darn cool, because then you have something, a relationship between things inside. Usually f's, you don't know where they're headed, like how are they mapping stuff. But the things inside, you sometimes know the relationship between them. So this is the first problem, and now let's do the second problem. So we have this problem, we're in the integers. How are we going to go about this? Well, the first thing is like we have some values given, right? We have f of 1, we have f of 2. Let's see what happens when we plug these in. So I'm plugging these in, we're trying to see like whether we get some other values from there. So plugging in, say, let's say n is equal to 1. What does that give us? That gives us f of n plus 2 is f of m plus 2. I don't see much value in this just yet. Now what if m is equal to 1? Then we have f of 1 plus f of n is equal to f of 1 plus f of n. Now this gives us f of 2 plus f of n. And this thing right here gives us f of 1 is 2, and then f of 2 is 4. This gives us 4 plus f of n. And now here, I would actually invite you, to pause for a bit and actually see if you can push the problem further from here, if you can figure if this gives you something, or if it doesn't. Pause now for the next 5-10 minutes, try to push the problem further. Here's the next idea. The idea here is like, wait, now from this, if I plug in, say, n equals 1, I'll get 4 plus f of 1 is 2 is equal to f of 2 plus 2 is 4. Now I have f of 4 is equal to 6. If I plug in n equals 2, I'll get 4 plus 4, which is 8, is equal to f of 2 plus f of 2 is 4, 2 plus 2, 2 plus 4 is 6. Actually, wait, I'll get f of 2 is going to be equal to, 4. And then I'll get a 6, I'll get f of 6 is equal to 8. Right, I'm getting some values now. Can I get other values? I invite you to pause for the next 5 minutes, see if you can get some other values, and the answer is you can basically get all the even values now from this thing right here. Because you're going to prove that f of 2n is going to be equal to 2n plus 2 for the even values. This is true for n equals 1, 2, 3. That's what you proved now. And now, assume it's true for some n, we plug in instead of assume this is true for some k. I usually like to switch up the names of the variables because it can get confusing. What am I plugging in? What am I assuming? Is equal to 2k plus 2. And then if I plug in instead of n, I'll set n to be equal to 2k minus 2. And what do I get? I know that f of 2k minus 2 is 2k as well. And then I'll have, and here's the reason I know this is because my base case is, I have 3 numbers in my base case. So I can go back to in my inductive hypothesis. So I know this thing to be true. And when I plug in here n is equal to 2 and m is equal to 1, I'll get that f of this is 2k plus 2 is going to be f of 2k plus 2 will be equal to 4 plus f of n will be equal to 4 plus f of this is 2k. In other words, f of 2k plus 1 is equal to 2k plus 1 plus 2. And so we've proved the inductive hypothesis. And now we pretty much have all the evens. Now what do we do with the odds? I invite you to pause for 5 minutes and figure that out. And the answer is, given we haven't used so far that f is injective, we should think about how we're going to be using that. And the answer here is, let's look at the two sides of the function. This side, if I switch m and n, I get the same thing. But here I don't. I get different things depending on whether or not I switch something. So that's important to keep in mind. Also, what have we found so far? We've really used that 4 plus f of n is equal to f of n plus 2. Right? We've really used this fact repeatedly to get to somewhere. Now, actually f of n plus 2. Now the question is, how can we get to the odds? How can we get to the odds? And also, let's first use this fact that this is symmetric and this isn't. What do we get? We get that this is also equal to, if we switch m and n, f of n plus f of n. And now what does this equality give us? Well, it gives us that f of n minus f of n is equal to f of m minus f of m for every single pair of integers m and n. What do we know from here? Well, you fix one of these, you say n is equal to 1, and you'll get a thing that holds for everything. So if we fix, say, n is equal to 1, we'll get this is 2, this is f of 2, which is 4. We'll get that 2 is equal to f of m minus f of m. And now we know this thing right here is true for every single, it's true for every single even one. We've already done that. But it's also true for every single odd m. And can we use that fact in any way, shape, or form, keeping in mind the function is injective, which means that every odd integer can only map to odd integers because all the evens are taken. F of 1 is 2, f of 2 is equal to 4, and so on. All the evens are taken. What is happening with the odds? I invite you to pause for another 10 minutes and see if you can push this problem further. Keep in mind this is an injection. And here's the next step. Well, we know that all the odds are going to be in the odds except 1. So the thing about natural numbers is we're having a subset of the odds. We're looking at where the odds are pointing to. And of all the members they're pointing to, there's the smallest one. Now, why do we pick the smallest one? Well, if that is some 2p plus 1. And we have f of, say, 2k plus 1 is equal to 2p plus 1. What do we get from here? We get that f of 2p plus 1 minus 2p plus 1 is equal to 2. In other words, f of 2p plus 1 is equal to 2p plus 3. And then we plug in 2p plus 1. and we get the next number. So we have f of 2p plus 3 is then going to be equal to 2p plus 5. And then starting from 2p plus 1, we're going to have all the other odd numbers will be taken. However, if this means that the numbers starting from 2p plus 1, so numbers 2p plus 3 and so on are taken, where p is going to be, well, p cannot be 0, because if p was 0, then we would have f of 1 is equal to 3. So other than that, p can be 1, 2, but say p was 2. What would that give us? That would give us that f of 2k plus 1 for some k is equal to 5. And then we'd have f of 5 is 7, we'd have 9 covered, and we would have f of everything, but we'd never get to f of 3. And f of 3 would have to be an odd number, so it would have to be the smallest one, which is 5. Now, the question is, can we actually figure out what this 2p plus 1 needs to be? What happens if, say, 2p plus 1, if p is greater than or equal to 2, and this actually not greater than or equal to 2, but say that p is greater than or equal to 3. What happens if the smallest number is a 7? Well, then we'll have that f of 7 will be equal to 9, f of 9 will be equal to 11, and so on and so forth. And the question is f of 3 and f of 5, what are they going to be equal to? Well, they can't be equal to any one of these numbers, and there are no odds left for them to be equal to. So they will have to be equal to the same thing, which is a contradiction. They'll both have to be equal to 7, which is a contradiction. So if we say, so now what's a good way to write this down? I invite you to pause for 5-10 minutes and think about how would you write this down. And the answer is, so we first say let f of 3 be equal to this, right? And then starting from this 2t plus 3, everything is settled, right? Starting from for n equals, for f of n, for n greater than or equal to 2t plus 3, we have f of n is n plus 2. Then this is settled. Now the numbers, f of 3, f of 5, all the way till f of 2t plus 1, are all odds, and none of them can be equal to 1. If any one of them was 1, we'd have the thing from beforehand. We'd have 1 here and a 2 here. We'd have 2 minus 1 is 2, which is wrong. And none of them can be equal to themselves. In our case, we'd have x minus x, which is 0, is 2. Again, that's wrong. So these numbers are going to be 5, 7, all the way till 2t plus 3 in some order. There's a 2t plus 3, yeah. 2t plus 3 in some order. Take the one which is equal to 5. And because they have to be odds, and these are the only odds, and they can't be equal to any one of these that are greater than 2t plus 3. So they're this. Take the one which is equal to 5, and then you will have, let f of k be equal to 5, and then you will have f of k plus, then you'll have f of 5 is equal to 7, f of 7 is equal to 9, and you'll have all these numbers set up. So that leaves f of 3 needs to be equal to 5. And so the solution to the functional equation needs to be of the form f of 1 is 2, and f of n is n plus 2 for all n greater than or equal to 2. And now we need to actually check this. So where is the original function? So this is the original function. If both m and n are, what's it called? If both of them are greater than or equal to 2, we'll have this one. So if mn are greater than or equal to 2, we'll have this is going to be n plus 4 plus n plus 2 is equal to f of n plus 4, which is going to be n plus 6. These two are equal. If m is equal to n is equal to 1, we will have 2, 4. We'll have 4 plus 2 is equal to 6, which is true. If m is 1, then we have that, and n is greater than or equal to 2, we'll have f of m will be equal to 4 plus n plus 2 is going to give us f of n plus 4, because f of n is n plus 2, we have n plus 2, we have n plus 4, which is equal to n plus 6. This is true. And if n is equal to 1 and m is greater than or equal to 2, then we will have that, what's it called? Then is 1, m is 2, then this is 2 plus f of m, which is m plus 4 again, is going to be equal to m plus 6. It's the same thing here. This shows that this function, if it needs to be this function, actually does work. And this finishes up our long problem and the introduction to our functions. I'm going to have one more video on the introduction, trying to work more with bijections, another problem. And from then on, I'll create a playlist which you can watch to actually, if you want to just like focus on functions from easier difficulty to harder difficulty, I'll set it up. So this finishes up the problem, and as always, thanks for problem solving.